Hi. A couple days ago, I was scrolling r/control theory, as one usually does, and I came across this question: how do you reduce a second-order equation to four first-order equations? Which piqued my interest because um, there's a lot of implications if I want to answer this that I would have to make, or assumptions. For example, um, are we talking about linear equations? And I think OPE means ordinary differential equations, but that's not entirely clear. And also, if you have a second order differential equation, linear, um, I wouldn't even know how to write four first order equations out of it because you only need two. So, what I think OPE means, if you have two first order linear, so if you have two second order linear ordinary differential equations, how do you write it as a system of four first order linear ordinary differential equations? Uh, which is kind of a mouthful, but I will show you later what that actually means. Um, and some people answered it sort of, but they don't really give a step-by-step guide of how to do this. It's kind of a lot to do on text. So I said, you know what? I've seen this multiple times now on this sub recently. Why don't I make a YouTube video about it? Which was, yeah, yeah, it was received quite well. So that's just what I'm going to do. But before we start, I need to say I'm going to make some assumptions in this question. So first of all, I think everything is linear. And secondly, I think we have two second order ordinary differential equations. So combining that fact, oops, we would have something like z double dot equals to z dot plus 3z, and another equation y double dot equals, what shall I take? Y dot plus 4y. Now, how many dots there are and what these factors are in front of your variables, it really doesn't matter. The only thing that is important here for our method is to have the single highest differential on the left-hand side, and then all the rest on the right-hand side for each equation. And also, it's best to have a factor of 1 here, so nothing. And then also, what I want to add is that this is not a mathematically sound way of doing this. This is just a method to get this done quickly. If you want to do this like actually mathematically well constructed, in this system you would have to look at the Jacobian, and typically if you want to extend it to nonlinear systems, you would take the Jacobian as well and then evaluate it at some x that you want to investigate, and then you would be doing linearization. But this is already linear, so we can skip that last part. But that would be how to do it mathematically correct. And this is just a quick and dirty method, but the results are absolutely guaranteed correct. So what we want to do is we want to find some form x dot equals a x, which we can do because this is a linear system. So, or these are two linear equations, so we can write them as one linear system. And this x dot already becomes what is on the left-hand side. That's the reason I said you want to write it like this, with the single highest differential on the left-hand side, is because then you already have this structure partially. And whatever is on the right-hand side, that just becomes your x. And I'm talking about the variables here, not the factors. So we can choose our x to be, let x be defined as, I don't know, z dot, oops, y dot, and then just z and y. Now I want to say you can pick any order. It's going to change what your A matrix looks like, but you cannot change your system definition. In other words, there's an infinite amount of ways actually that A and X can present themselves, but they're all correct as long as you don't make any mistakes. And naturally, if this is our X, then X dot would be Z double dot, Y double dot, Z dot, and Y dot. Now, we can substitute these two into our original equations. And then we would get, for Z double dot, that doesn't exist in our X. So we need to use our X dot, right? And I'm going to write this down as this is X1 dot, X2 dot, X3 dot, and X4 dot. And here it's just X4, X3, X2, and X1. That's just notation. I just call them like that, but they're still like the same variable. You could put in equals here. If you get what I mean, it's just I'm going to all turn them into X, basically. So then on the left-hand side, we would get X1 dot. See, Z double dot is our first entry in X dot, our first row, equals 2, and then we can look at X1, and Z is X3. So 2x1 plus 3x3. And for the second equation, we can do the same. And you can pause and think about it if you need to, but I'm just going to write it down. It's x2 plus 4x4. Yep. And then we have these equations. However, we want to write it in the form x dot equals ax. And in order to be able to do this, we need an x that is 4 rows. But because x is 4 rows, x dot also needs to be 4 rows. Now, if we want to find this formulation, that means that on the left-hand side, we are missing 2 equations. And on the right-hand side, we are also missing 2 equations. This fully substitutes into what we have here. And so in terms of just substitution, it would be a complete definition. But in terms of our linear system, we are just not yet done. So we need to find our x3 dot and our x4 dot as well. Wow, my handwriting really sucks. x4 dot, there you go. Now, the funny thing is that if you look at x3 dot, it's actually z dot, which already exists in our x, without the x dot, just our normal x. And the same for y dot in our x dot. So x4 dot is actually the same as just our x2. So here we just have x1 and x2. Now, this is the point where you just need to know linear algebra, is that if you turn these back into a vector, so you get x dot equals x1 dot, x2 dot, x3 dot, and x4 dot as one vector, then you can turn the right-hand side into a vector as well. So 2x1 plus 3x3, and then x2 plus 4x4, and x1 and x2. And now you see, okay, this is starting to look the right way, right? On the left-hand side, we now have our complete x dot. However, on the right-hand side, we don't have a matrix A multiplied by a vector x. We just have ax already combined. So can we split this up into a matrix and a vector? And the answer is yes, of course. It's all linear, so you can do a linear operation like that. Which would be if we have our x on the right-hand side, as we have it in our definition here, then what would we get? Well, the way linear algebra works is that if you multiply a matrix with a vector, you multiply every row of the matrix with the vector. So the first row times the vector x would be 2 times x1, and 0 times x2, and then 3 times x3, and then 0 times x4. And we can do the same for all the other rows, and then you would get 0, 1, 0, 4, 1, 0, 0, 0, and 0, 1, 0, 0. This would then be our A, and this would be our X. This would be X dot. And what we have here, you can do this for fun. You can do this multiplication now by hand, and you should find this AX already multiplied. Now, is there a faster way to do this? Yeah, of course, you can actually just skip a lot of steps. And I'm going to show you how to do that with just a very simple example. But the important thing that you need to realize is that whatever our variables are here with the order of differentiations, that's just going to be our x. And you can pick the order any way you want. What I always do is the highest orders of differentiation are my first ones in my x matrix, and then I work back towards the 0th order differentials. So z and y are just the last ones. Of course, sometimes they are not even included, like this could be a triple dot, and this a double dot, and this a single dot, and then z is not in there, and then z would just not be in here. But the point is that generally I tend to begin with the highest order on the right-hand side of the equation for my x, and then I just work back to wherever it goes. And I do that for both. And it doesn't matter if you want to do z dot z and then y dot y, or if you want to do z dot y dot z y. It doesn't matter. The way your A matrix will look like will just be a little bit scrambled with respect to what we have here, but it's still just completely correct. So that is how you can really quickly spot your A. But can you really quickly spot your, sorry, that's how you can really quickly spot your X, but can you really quickly spot your A? And the answer is yes, you can also do that. You see this 2 and this 3 and this 1, of course, there's no 1 here, but you could just write this 1 and a 4, 2, 3, 1, 4, they are already in here. Now, knowing what your X is going to be like, because you can just choose it as you want, you can find the corresponding factors that are here. And they will just simply be for the first row and the second row. They will be just the same factors here in your first row and your second row. And then whatever is underneath is just ones diagonally until you reach the bottom, starting on the left column underneath your rows with your factors. Then you just get a 1 all the way to the left, and you just go diagonally down to the right. with ones, and that's it. That's your structure. Now, I can show you a really quick example. For example, if we have z and then 4 dots equals z triple dot plus 2 z, 2 z double dot. You know, let's make this a 4, this a 5. I'm just going to scramble the numbers. And this is, I don't know, 10z. Right? This is a fourth order differential equation. Now, is that correct? No, wait. Plus z. This is what I want to show you. Now, I'm just going to do the procedure that I showed you before to really quickly get it. My single highest derivative is on the left-hand side, and then all the others are on the right-hand side. So I'm just going to pick the variables here. My personal preference is to start with the highest order and then work down. So x will be z triple dot, z double dot, z dot, and z. And then a will be with the corresponding order as we have it here in this equation. 5, 4, 10, 1. And then underneath the row with the factors, I'm just going to start with a 1. Sorry. This is a 10, not a 1, 0 here. And then I'm just going to work my way diagonally down. I'm making a lot of mistakes here. There you go. And this is your A and this is your X, and you're done. Now you can just say X dot equals AX, with X dot, of course, being Z 4 dots all the way till Z dot. And that is how quickly you can do this if you just see this general structure and realize that if you multiply a matrix with a vector, you multiply rows with a column. And so the first row of A with the first column of B will be your first entry in X dot, which if you pick your X this way, it will be your first row. And then yeah, you just get this equation out of it. You can sort of immediately see that now that it's here, right? And so if you do this a couple times, you will be able to see the linear differential equation and sort of immediately see the system that comes out of it. If you want to read up on this specific structure of a matrix, it's not really important right now. If you're learning this, then you probably don't even know why this is relevant and what it means. But this form of the A with a certain row here, and then ones on the diagonal like this, and then one column of zeros like that, is called companion form. And it has a lot of cool properties that are too complex to go into right now, but you could look it up on Wikipedia if you want. So that is generally what I wanted to cover. It's how to write a higher order linear ordinary differential equation, a scalar equation, into a first order system of linear differential equations. And yeah, I hope that answers your question if you're the poster of this post on Reddit, or if you're just generally interested in this, if you're a lurker. Yeah, and then I hope this served you in any way. Anyway, it's getting really late, so I wish you a good night. Bye-bye.